So here we're going to look at kind of basics for reactions, and then we'll look a little bit at balancing, just as a review of those terms. So to kind of start this off, I want to address this concept of conservation of mass. Lavoisier, cool stuff, made this observation, and we'll add to this when we bring in kind of Einstein, that when we're looking at these kind of principles of conservation, that neither mass or energy are created or destroyed in a chemical reaction. So we can convert them around, we just can't get rid of them. This principle in and of itself, there doesn't appear to be any obvious kind of mathematical system that comes out of it. So let's take a look at some examples where we can actually address some of the mathematical principles. Come on, technology. So if we were to say, look at a chemical reaction of hydrogen gas reacting with oxygen gas to produce water, we could say hydrogen plus oxygen equals water. What this law of conservation of mass is saying is that if I take 2 grams of hydrogen and I take 16 grams of oxygen, if this expression is correct, then I will end up with 18 grams of water, right? Conservation of mass. The total mass on the reactant side must equal the total mass on the product side. Okay, and that's really all this is trying to do. Okay, and this is neat and useful to a certain extent. One of the things that happens is that we start to overuse this, and that happens in a lot of cases. And we'll see an example of what I mean by that in a second. So the appropriate use, we could kind of backtrack out of this and we could say, well, how many grams of oxygen are needed to react with 2 grams of hydrogen to produce 18 grams of water? As long as we have this expression that shows us those relationships, we can effectively say 2 plus x equals 18, and now we can do a bit of algebra to solve for that x. That's the point of this. And that's pretty cool, right? Particularly that Lavoisier was able to figure this out. Some of the limitations that go along with this. If we look at, say, a recipe, okay, because remember, a chemical equation is pretty close to a recipe. A recipe to make a cake, some recipes measure by mass, but a lot measure by amount. What do I mean? You don't take 500 grams of flour, you take 2 cups of flour. So you're changing kind of the unit system behind it. Then probably the best example to use in this case would be to reference something like eggs. Okay? In a recipe, you aren't using 5 grams of eggs, you're using 1 egg. Okay? So a recipe tends to tell you not measurements, but kind of a counting effect. When we look at chemical reactions, they are full-on a counting effect. We don't do measurements where it takes this many particles with this many particles to make this many particles. Okay, so measurements aren't really a good thing to associate with chemical equations. So, but isn't that exactly what Lavoisier is doing with conservation of mass? Yeah, okay. And so there are certain circumstances where it works phenomenally well. We just went through one. But there are other circumstances where it doesn't work so well, and it tends to goof things up. So, for instance, if we look at the bottom one, we take wood plus oxygen to make a gas and water. We don't need to know the details about it necessarily. So let's say I take 4 grams of wood, 1 gram of oxygen. How much gas was produced? Okay. Usually, I'll get a shout out of, oh, it's 1 gram of gas was made. And I go, no, it wasn't 1 gram. They go, okay, well, then it was 4 grams. No, it wasn't 4 grams either. Okay. The issue with this mass thing is it's really only the total. I know the total reactants was 5 grams, and I know the total products has to be 5 grams. But there's nothing that says that this has to be 1 and this is 4, or this is 4 and this is 1. This could be 1.5 and 3.5. The exact distribution of that mass across those products can be wildly different. There's something else that has to be introduced to really figure out those exact relationships. And that's looking at the quantity, and that's really balancing a chemical equation. So when we're using conservation of mass, it is a useful idea to get across, but its utility really only comes into play in equations that produce one thing, or you start with one thing and you end with many. So it's easier to solve. We could still solve the 4-part equation that we've got at the bottom. It does get a little bit more challenging because you have to add or provide more information. So if I said 4 grams of wood, 1 gram of oxygen, and I want to know how much water was produced, well, I also have to tell you that you had 3 grams of gas. Okay? So in these more complex equations, we end up having to supply so much information behind it that it kind of devalues that question, okay, as far as an exam question goes. In an actual experiment, you would know a lot of that information and you could kind of back calculate things. And you'll see that, or you would see that if we were in person in first semester general chemistry, so 151. We do experiments that play with this. But be very, very careful associating mass with a chemical equation. It's usually a very bad association. Okay? So what's happening during this chemical change is that we're shuffling those pieces around. Okay? So each of the molecules, not the mass of that molecule per se, but that molecule around. Okay? And this is where Proust was able to kind of add to this and saw that we got definite compositions. That if I looked at water, it always had 2 parts hydrogen to 1 part oxygen. Note, I can get away with parts because I can say atoms or grams and it'll work out. No, grams doesn't work. Never mind. That doesn't work. It contains the same proportion kind of regardless of what happens. So if I look at water with H2O, I have 2 hydrogens will always pair up with 1 oxygen. So that ratio is constant. If I switch it to mass, I can say 2 grams will always pair up to 16 grams. Okay? Note the numbers change, but the ratio for water will always maintain that. So if I had a sample that had 4 grams of hydrogen in it, I also know that it has to have 13 grams of oxygen to maintain that ratio. And yeah, I did that right. Right? So Proust was able to kind of build this. That law of definite composition I find kind of fascinating because how was he able to kind of figure that out and piece that together? Right now in the modern world, we've got the ability to look at all different compositions and say, well, it has this many atoms and that many atoms. But this is black and white. That's not even a photograph. That's a hand-drawn image of the dude. That's how old these discoveries were. And so I kind of wondered about that. And so that's why this is here. You can look at particular samples or study not all chemicals, but particular chemicals have very predictable reactions. So for instance, potassium perchlorate will decompose into potassium chloride and oxygen gas. So we can look at that particular equation, the KClO4, KCl plus O2, and I can use conservation of mass to prove that that's the case. Okay, and so that's kind of the neat thing, is that we just have to get a little bit more selective in the reactions we look at. We can look at electrolysis to force reactions. We can also do careful design of combustion reactions, which is neat. Okay, but kind of beside the point, that's all neat, but what is it useful for? Well, that use is really where now Dalton takes all of that information that's been collected from hundreds of years of research and now puts it all together into what we talked about before with our atomic theory. And as we addressed, he wasn't perfect with these, but he took it leaps and bounds further than it was before. Remember, we started with mass, right? Well, conservation of mass. But if we go through and look at Dalton's theory, okay, where we're starting is he's not referencing mass, he's talking about atoms that make this up, okay, a small particle. So he's kind of nuancing that difference between mass and amount. And yes, there's a relationship, but if I'm looking at a chemical equation, the amount or the number of those particles becomes more important. Okay? And that's a really kind of neat, kind of leaps and bounds advancement for how we can now look at chemical reactions. And that's cool. Okay? Then Thomson, Rutherford, all them come in and say Dalton's couple theories don't work, but that still the underlying thought and mechanism behind them does. Okay, and it's that application of it and building and improving those old theories that's really what science is about. Okay, so excuse me, let's push this to a chemical reaction. So right here in that goofy font, we've got solid sodium hydride reacting with acetic acid to produce aqueous sodium acetate and hydrogen gas. What you should be able to do at this point, because you've done nomenclature, is take all of that text and now convert that into a chemical equation. Okay? And that's challenging, but let's take a swing at it, which I think I already did in one of the videos. But let's start. Of course, we don't read linearly. Sodium, Na, hydride, H, solid, S. Okay, so we're coding that information as we move through this. Reacts with is now our plus. Okay, acetic acid is an interesting one, and I'll try and pull this out. Acid tells us that we have H and that we have a Q. The acetic part, C2H3O2, we know all that because it's an acid. And note that the acid moniker is what's giving us the phase. I don't have to explicitly say that this is aqueous because, at least as far as you're concerned, acid means aqueous. The next part, to produce, gets us a reaction arrow, and because I drew it horribly, we're going to split the line. Okay, we move to the next one, sodium. There's our Na. Our acetate is that acetic, C2H3O2. We've got our phase being given to us, aqueous, and is our mathematical operator. And then we get hydrogen gas. I'm not quite sure what color to draw that. So we'll just go with hydrogen and then gas. Oops, get another little color in there. Gas. So there's kind of our assembly of this, if you will. Based off of our nomenclature skills, once we've done this initial kind of placement of pieces, we should go back and look at each piece and be like, did I actually put that together right? So sodium has a +1, hydride has a -1. That formula was correct. Okay, and I'll do the sodium acetate. Sodium has a +1, acetate I'm required to memorize has a -1. That formula is correct. So when I translate from the English down, it's not just what are those symbols, but then also I have to ensure that I'm getting the proper alignment of those symbols with each other, which is really going to leave us for this last piece, for hydrogen gas. Okay? Nothing about that name suggests anything else, and based off of the nomenclature we've addressed so far, just charges, shouldn't that be a +1? Well, that charge information should be specified in the upper right-hand corner, okay? And we didn't write anything there. We didn't write anything there because we know it's not a +1. Because if it had been a +1, it would have been an ion, and I wouldn't have said hydrogen gas, I would have said hydrogen ion. Okay, so what's going on with that? What is its charge? And is there, say, perhaps another piece of information that's missing? Yes, it's not just H, it's H2. Okay? In the other cases, the numbers of the atoms that go in are characteristic either for that species, acetate, or the number of sodiums in sodium acetate is because I'm dealing with a charge imbalance. So why is hydrogen gas H2? Well, it turns out that certain elements are what are known as diatomic, right? And we are required to know those so that when we reference hydrogen gas, we know it's H2. Just like when I say acetate, we know it's C2H3O2 negative. All of that information is encoded in that name, and we have to know it. Okay? So there are certain elements that are diatomic. Okay? Those certain elements would be hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So you have to know those 7 elements. Okay? When it comes to memorization, you've got to use whatever works for you. And so there are some mnemonic devices that I happen to know for memorization, and when I reference them, I'll let you know what they are. This happens to be one. In fact, I know now multiple of these for this one. Okay, so we have to know those elements. So let's go through and identify those. We've got hydrogen, then we said nitrogen, oxygen, fluorine, chlorine, bromine, iodine, okay, which happen to be 7 elements that are diatomic. Well, this shape right there happens to look like a 7. Well, look at that. Okay, if we just find the correct 7, and that becomes a challenge, but the correct 7, we now have our elements memorized. Except I've only circled 6. Oh, there's the 7th. Okay, so that potentially works as a memorization technique. The other one, which I was surprised to have learned about in the state of Arizona, since I figured no one here would know anything about like ice, this shape looks kind of like a hockey stick and a puck. For those of you who don't know what a hockey stick is, right? It's used in ice skating or ice hockey to hit a little puck around, the ground, and you hit it into the opposing person's, goal net. Go sports. Okay, so we've got a hockey stick and a puck to help with it. And then, of course, all the way back to high school, my favorite, childish, I know, but it is what it is. Have no fear of ice cold beer. Okay? Which is a classic kind of memorization technique. You turn the things that you're trying to memorize into a story or words that you'll have a better time of memorizing. And because in high school, clearly I was super, mature, ice cold beer. Oh man, that's awesome. So there we go. Have no fear of ice cold beer. And the associations with it would be the letters in each of those statements. Have, hydrogen, N, nitrogen, fear, fluorine, oxygen, O, oxygen, I, iodine, cold, it's not perfect, Cl, cold, as opposed to carbon, so chlorine, and then beer, bromine. Okay? So it kind of nails down those pieces. So anytime you see one of these elements named, it is immediately diatomic. Every time. So if I say, hey, I'm looking at oxygen, I'm referencing O2. How do I know I only want to look at, say, a single atom of oxygen? How do I know the formula I want is just O? Well, actually, I already said it. I would know I'm looking at a single atom of oxygen because I would say atom of oxygen. That's how the term comes out. So when you hear oxygen, it's diatomic. When you hear nitrogen, it's diatomic. The only time it isn't is when we explicitly state atom of, okay, or single atom of. Okay? If we reference molecules by definition the combination of them, which then means we would be diatomic as well. Okay? We will see questions like that pop up in the 3rd unit when we start running some calculations, because when we get into our calculations, we have to be a little bit more careful about the unit that we talked about, which is a number, then the measurement, and then the substance. And if our substance unit is mislabeled, the whole thing crumbles. Okay, so it will become important again. I just put this up again. You should have seen it already in the play posit. This is our guidelines for balancing. Okay, I did add a couple things, and doesn't look particularly clear to me right now, but these first two steps are kind of additions, if you will, on balancing equations. Balancing equations really just starts down here. Okay, this is really your balancing. Okay, but you have to make sure that these first two steps are done correctly. So when we look at predicting products, sometimes you are expected to predict the product. Okay? That sometimes is 4 out of the 6 reaction types. And we may not force you to predict them. We may give them to you. Okay? So you have to look at the question and be careful with it. The next part is that you have to make sure that each of the formulas that you have written are correct, which is what we did when we looked at the sodium acetate, right? Sodium and acetate, their charges canceled out. So we're using our nomenclature rules to ensure that we have a proper formula so that when we go through to balance, we can balance the equation properly. Okay? So those first two steps are very commonly forgotten, and particularly the second one, okay, number 2, because that's involving that kind of balance out of those charges. And that is a challenging concept. And that's the important part in nomenclature. I could care less if you learned how to name a compound, because that's not that big a deal to me. What I care about is, can you manipulate that structure in further things, which means you have to have a proper structure. That requires balancing your formulas correctly. That's the important part in nomenclature. Knowing that Na is sodium, meh. If you say Na, most chemists are going to be like, you mean sodium. There's not a communication barrier. Okay? The communication lock that's really going to happen is if you can't associate those charges properly, then everything's going to fall apart. Okay? So make sure you practice your nomenclature and balance those formulas properly, because if that's broken, balancing chemical equations will also break. Okay? The last thing I'll draw your attention to on this is that 6, or what I call step 6, you need to check your work. My general rule for checking work is that you should check it so many times that you are irritated that I have asked you to check your work. You can get mad at me as much as you want as long as you get the answer right. Fair enough? Okay. So I will make you do things so that you get the answer right. You can get mad at me for making you do it. Get the freaking answer right. You don't do that practice that I tell you to do. When you get the answer wrong, I'm just going to be like, I told you so, and I don't want to do that. I really, really don't. Okay? I'd like to see you get the answer wrong. So this came up in the play posit. I asked you to go through and balance this equation. Theoretically, you've already done so I won't even bother to say, pause the video, and we can go through and set up our work behind this process. Because I've been having fun doing this. Let's go ahead. That's a pretty good ringer there. Okay, so I want to go through and establish my process. Okay, according to my steps, I want to balance one atom at a time to go through this, and I'll start with aluminum. Why did I pick aluminum? It was the first in the list. When I look on the reactant side, there's 2. When I look on the product side, there's 1. Now, before I continue the way I would do it, I have oftentimes seen then students go, well, barium, there's 1, barium, there's 1, and they go through and list out all. No, don't do that, because all you end up doing is writing redundant information, okay, or what could become redundant. Once you pick an element, balance it. 2 is not equal to 1. I will fix that by changing the coefficient on that side. That makes this 1 a 2. Okay, no, I want to show that work. I want to show that arrow. I want to see those pieces so that I can check my work later. I would probably jump to barium next, okay, and that's because it's simple, quote unquote. Okay, the barium is simple because if I look at the other pieces, I've got sulfur with oxygen and I got nitrogen with oxygen, and that's just going to be kind of confusing. So I'm going to jump to barium. Look at barium, we said 1 and 1. Okay. Now I've got to double back to the difficult path. The difficult path can have some outs. Okay, so the first thing that I could go through and do is I could go through and say, well, I'm going to balance by atoms. So I could look at sulfur. And if I look at sulfur, I have 3 on the reactant side, and I have 1 on the product side, right? This 3 applies to the parenthetical, which means that is SO4, SO4, SO4. It doesn't apply to the aluminum because the parentheses came before it. And this would be aluminum, aluminum, like that. So that doesn't balance, so I need to make this a 3, okay, so that the sulfur would balance. Okay. Next thing, you may notice, well, now the barium has changed. Irrelevant, I don't care. I'm going to continue through balancing the rest of the equation. I'm not going to start doubling back because that doubling back process can lead me into confusing paths. I'll now move to the nitrogen. Note, I'm going to skip oxygen for this moment because the oxygen shows up in a bunch of different places. If it isn't already balanced, it's going to be crappy to balance. So I'm going to leave it alone. The nitrogen on the left-hand side, 2 times our parenthetical, means that I have 2 nitrogens. On the product side, I have 3, but 2. What does that mean? That doesn't mean 5, so let's walk through what this means. So our formula was Al NO3, 3. But then I had a 2 out front, which means this needs to be repeated times 2. How would I repeat it times 2? Well, Al NO3, NO3, NO3. Okay, all of that information is stashed in there, which means now when I look at my nitrogen, 1, 2, 3, 4, 5, 6. I have 6 nitrogens. My nitrogen is way unbalanced. Okay, so to fix that, I need to go back to the reactant side. For that to become a 6, I would need to multiply by 3. I can put my 3 there. Okay. Now I could go through and attempt to balance my oxygen, drop my oxygen, and this is going to be exciting here. So if we look at our oxygens, there's 4, 8, 12, right? Plus, in this case, I had NO3, but then I had 3 sets of those. So repeated calculations, I had 6 times 3, 18. Which would give me a whopping total of 30. And then I think zeros with a slash through it because we got the oxygen there just to be confusing. If we look at our other nitrogen, we had 3, 6, 9, 12, 15, 18. And we had 4, but 3 sets of those, which would be 12, which is going to get us to that 30 again, which means the oxygen was balanced. Okay? I have changed a lot of numbers. Okay? So I've continued through my entire process all the way down to make sure everything was balanced. Now what should I do? Oh, horror of horrors. Okay? At least in the horror of horrors in the sense of all this work as I'm erasing all that stuff I've written down. For you, you would just rewrite it and you would start again. Aluminum, 2 on the left, 2 on the right. I attempted to color code before, let's keep it up. Okay, barium, 3 on the left, 3 on the right. Okay, and now I'm actually going to throw a little kind of side kink into this to mess with this. Okay, in that mess with it process, when I go through and look at what color do I want here, we'll go ahead and do purple. Sulfur, I can actually balance it as SO4. I don't have to balance it as sulfur. And the reason being is that when I look at the product and I look at the reactant, they both have SO4. As long as it doesn't change, I can keep that grouped, which simplifies things because that's now 3 and 3. I can do the same thing with the nitrate, NO3, 6 and 6, and now it's balanced. And I don't have to count as high with all those oxygens getting up into that 30 range. And so that simplifies my work. One of the things that I forgot to call attention to as we went through and did it is that we'd initially said that our sulfur didn't align, which messed with our bariums. We continued the process downwards instead of doubling back. If we had doubled back, we would now be backtracking over our process, and we have increased the odds of mistakes. If we just continue all the way through, what happened? It fixed itself. The bariums balance themselves out, right, by making an adjustment with the nitrogen or with the nitrogen later on. Okay, so do an element, do the next one, do the next one. If you note that a number changes, that's okay. Do not backtrack. Continue through your process. Once you've gone all the way through, if you've changed any coefficients, start again. When you've gone through and you haven't touched the coefficients, then you're done. There's no need to check it again because nothing has changed. Now you could go through and answer questions based off of your balancing process. Okay, what kind of questions could you get? I could ask for, what is the coefficient on barium nitrate? Okay, barium nitrate was the BaNO3 so our answer would be 3. That would be its coefficient. Okay, the coefficient is merely the number in front. I could ask for the sum of coefficients. Okay, so that would mean our 3 plus our 2 plus our 3, and then this is usually where it gets tricky, plus 1. Remember, just because you didn't write a number there doesn't mean there's not an implied 1. Do you need to write the 1? No, it is not a requirement. Okay? However, in the case of being asked the sum of the coefficients, if you write a 1, do you increase the odds that you will always add it in? Yes, then you should probably write the 1. Okay? So it doesn't hurt to write the 1, and for that reason, it kind of makes sense to include it. Okay? So with that, we've now balanced, and we've hit the end of our video. Hopefully that worked out for you because we addressed kind of multiple ways that we could look at those balancings. If you encounter questions, feel free to send me an email, talk to me, practice, 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 and you'll be a rock star at this.